Welcome to the video. In this video, we'll talk about binary search, what it is, and how to use it. When I think of binary search, I think back to one of the first courses I took when I started programming. This course was Harvard's famous CS50. And if you've ever seen it, I recommend that you check it out because I think it would be a great refresher on occasion. Nevertheless, getting back to why I think about this class when I hear binary search, within the first month, David Milan teaches the class about algorithms and Big O notation. During his explanation on binary search, he rips a phone book and demonstrates how binary search works. I think it's a good image to get in your head. So let's take a look.
Nice to meet you. And you were here with us in week 0, of course.
I was.
So could you go ahead and find for us Mike Smith as fast as you can? As fast as you can. Literally tearing the problem in half as you need to. Just literally tearing the problem in half.
Very good.
Okay, good. Thank you.
Very good. Okay.
And so now you've whittled it down to half the size of the problem. Now we're down to a quarter. Are you paying attention to which side we're keeping?
Yes, I think.
What section are we in?
Mufflers, so here we go.
Okay, but Mike Smith is going to be after mufflers. So all right.
Where are we looking?
Mike Smith.
Mike Smith.
Now we're in surgical. Now physicians. Now
let's go.
Okay. Real. Okay, if you need real. Now which way is Mike Smith?
This way.
Which way?
Wait. Emma's right. We're starting with.
Yeah, they're left. You're right.
Yeah.
So Mike's in here.
What? Bad example, guys.
We'll
Sorry.
teach you to leap out of your chair.
Oh! I got you. Oh. This is okay. I got you.
Okay.
Smith right here.
Smith, thank you. So I'll keep looking up for Smith.
Oh yeah. No. Oh no. This is mine.
Oh, you got Smith.
I
Okay.
got Smith right here. Sorry, guys. I thought Michael. We were looking for Michael. Sorry.
It's okay. All right, where are we in? Now we're in Pacini and Sons.
Pacini and Sons.
Only you and I are in on this. Okay. All right, find us Mike Smith. Smith. We're in R for rubbish.
Rubbish. Oh. This is gonna take a while.
Okay. Yeah.
Okay.
Shoes. We're in shoes.
Now we're gonna.
Nice.
Which? Oh, this is great.
It's okay.
Oh, this is good. I don't think I'm gonna have peace at buddies after this.
No. Good. Sporting.
LMNOP.
Okay, so let's tear this in half. You know, it's okay. This ends poorly anyway because Mike Smith won't be in the yellow pages.
Oh.
No, it's okay, but let's pretend like he's on this page. So now you've whittled the problem down to one page, and we found Mike Smith. Okay, thank you. Still faster than linear search, wherein we start at the beginning of the book and we move our way from left to right, eventually looking for Mike Smith. And so if the phone book had maybe 1,000 pages, maybe it would have taken us 10 or so page tears. But you may have leveraged an assumption during all of that, which is to say that the phone book in advance was what? It's sorted.
So binary search finds an item in a sorted array, and this is important to keep in mind. Just like the phone book, anything that uses binary search must be sorted. A binary search algorithm finds an item in a sorted array in O of log n steps, or you can say order of log n steps. If we just turned each page and did a brute force sort of search, we would end up with a time complexity of an order of n. Meaning if we would have to check every element in O of n divided by 2, we would flip through every 2 pages. You can see where this efficiency lies. Basically, log states that log n is equal to the quantity which 2, our base here, needs to be raised to. Let's look at a quick example. I will eventually do a video on Big O notation, but here's a quick refresher and a rundown with an example problem. We are given an array here with 16 elements. Notice that it's sorted. That's important. Don't forget. Our target is 13. So we have to efficiently search through the array to find the value. Efficiently regarding the amount of time or steps it will take us. The first step is to split the array into two, right down the middle. To do this, we can take the length of the array and divide it by 2. Our length of the array is 16, and we divide that by 2 to get 8. Now that is split. We check to see if our target, 13, is less than or greater than our middle element. And in this case, it's less than our middle element of 16. So we can throw away the larger values and continue splitting up the lower value array. Next thing to do is split the array evenly again by dividing by 2. Now our middle element has become 8, and therefore we can toss out the smaller values within that array. We are left with 4 elements in our array, and again we split that down the middle. When we split down the middle, our middle element was 15, and therefore that portion of the array will be tossed, leaving us with 2 values, 12 and 13. We are splitting and comparing, and so on. We split again to be left with our target of 13. And that's that. Now to generalize this formula that we use to split our array, we can say that n is the number of elements and k is the amount of steps used to complete the splits. So this is saying, how many halves or splits are there? How many times must we divide our original array in half until we get to 1? We can simplify this formula in order to help us format this easily into a logarithmic format. Comparing it or simplifying it even more to a logarithmic form, we can better understand this. So here it is, n the number of elements within our array, and k the number of steps used to split can be seen with meaning. Just remember, we are looking at the number of times we must divide n in half to get down to 1. This algorithm takes log n steps in the worst case. When we have to check 16 elements in an array, n might not seem all that much bigger than log n. But if we have a 4 billion indices array, the difference really does matter. And in that case, linear search would take 4 billion steps in the worst case, while binary search would only take 32. A huge difference in efficiency there. We can now see that binary search algorithm takes a divide and conquer approach, where the array is continuously divided until the item is found or until there are no more elements left for checking. We can see this algorithm can be defined recursively to generate our solution. And the two base cases for recursion would be no more elements left in the array and when the item is found. Let's move over to Python Tutor to take a look at the code that we can use to solve this problem. We should write some steps here to help us outline the code, some pseudocode, if you will. There were 4 basic steps we used to compute this manually. The first one was compare the target with the middle element. The second step would be, if the target matched the middle element, we return the middle index. And in that case, that would be a lucky shot. But if we're not lucky, then if the target is greater than the middle element, then the target can only lie in the right half subarray after the mid element. So we have to recursively start at step 1 again for the right half. Now, if the target is less than that middle element, we have to recursively start at step 1 again for the left half. We can define our function here with the parameters array, left, right, and target. Since we will be using recursion, we can start with our case base as well. So here, if the item is found or if there are no elements left in the array, we're going to return whatever that middle index is. So if the item is found or if there are no other elements left in the array, we are going to return this middle index. Now we have an elif statement. This is going to say if the middle element is greater than the target, we're going to keep the right half subarray and then return to step 1. So here's our recursion. And if we have one for the right, we're going to need one for the left. So our else statement will deal with this left half subarray. So if the middle element is less than the target, we want to keep that left half subarray and then return to step 1, do our recursion again. Now, let me just talk about the left and right parameters of this function here. The left parameter is always going to be the first index. So with whatever we're dealing with here, the left is always going to be the first index in our array. And it could be the array or it could be one of the subarrays, but it's always going to be that first index. And then the right will always be the last index. And we always have to subtract 1. Don't forget to subtract 1 here. But this is what's happening in these conditional statements here. So here we have the middle index minus 1, and we have that on the right side because that's the side that we want to keep. Here we're going to have middle index plus 1 because we're going to want to keep the left-hand side, and we're going to need to sort of identify that first index. All right, so in order to call this function, let's go ahead and define an array here. So our array here has 5 elements within it, and our target here will be 10. So we're going to be looking for 10 as the target. We will call this function within result, the variable result. And this way we can just display it here with a print statement indicating whether our target is present or whether our target is not present. And just to go back to these left and right parameters here. So the left, we're starting with the original array. So this left parameter is going to be the 0th index. And now the right parameter will be the length of that array minus 1. So it'll be the 5th index here. Well, actually 4th index. All right, so let's visualize this execution. All right, first within the global frame, we are loading our function. Here's our array and target. And now let's jump into our function and see what we have. So now this statement, this is our base case again. If the right is greater than or equal to the left. All right, in our original array, the right is always going to be greater than the left. So it will run the next line in that conditional statement where the middle index, now the middle index will equal 2. And we continue. Now in the index of 2, so the value of 4, now we're in the index of 2, and we're going to check, well, did we get lucky? And did we say that middle index was where our target was? And no. And therefore, we'll move on to that next conditional statement. All right, and we'll keep moving through this function here recursively, calling a return statement if there has not been any base case conditions met yet. And once the function has run into the base case, prints out the output. And the output here is index 3, and that is where our target lies. So just to show you that the length of the input array will not affect how we find the middle, I'll just go ahead and throw another element in there. We'll visualize this execution, and we'll see that it does still find that target in index 3. So that's the video. I hope you guys got a good refresher on Big O notation. More to come on that. And a nice refresher on binary search. All right. Hope you have a good one.